Hello everyone. Today we are going to take a case of Fourier series where the range is minus L to L. Before I start with this minus L to L, let me take some recall part that we have already done in the earlier lectures. There can be, whenever the series range is minus pi to pi or minus L to L, first thing we check whether the series is even or odd. So to check whether the function is even or odd, we replace x with minus x. If the function remains same, it is even function. If we replace x with minus x and if we have an extra minus sign or a multiplying factor minus 1, the function is said to be odd. If the function is even, then for the Fourier series, the coefficient bn becomes 0. A0, the formula is 2 by L 0 to L f of x dx, and an formula is 2 by L 0 to L f of x cos n pi x by L dx. Same concept we have taken for minus pi to pi. For odd, a0 and an is 0. Only we need to find this bn. You can pause the video and write the formula in your notebooks. I hope you have written the formula. Now let us begin with a simple sum. The question says, find the Fourier series for f of x is 1 minus x square. The range is minus 1 to 1. Okay, so now the range is minus 1 to 1. So here the value for L, the value that is minus L to L, a constant number. So the value for L is 1. So in the formula, wherever L is there we'll substitute 1. Before using the formula, let me find whether f of x is even or odd. To identify whether f of x is even or odd, in place of x, substitute minus x. So when I substitute minus x, you know that minus of x is plus x square. We can easily check that f of x is same as f of minus x. So whenever f of minus x is equal to f of x, we can conclude that the function is even. So if the function is even, then what is 0? Correct. Your bn is 0. So what we will find for this now? We'll just find a0 on an. So let us write the formula for a0. 1 by L, you can write minus L to L. This is one of the formula. Or you can write 2 by L 0 to L f of x dx. We have seen this because for even function, minus a to a can be written as 2 into 0 to a. So let us substitute the value for L, that is 1. And f of x, it is 1 minus x square. So integrating this, I get 0 to 1, and solving this, the final answer is 4 by 3. So the value for a0 is 4 by 3. Similarly, we'll find the value for an. The value for an, again, the formula can be this. Or you can write the same formula as 2 by L. Any one, whichever is comfortable or whatever you can remember in the exam, that you can write down. So by both the formula, you'll get the correct answer. Let us substitute f of x. Let us substitute the value of L. The value of L is 1 as we've seen earlier, and f of x is 1 minus x square. Now what we will do is, this is shortcut method u into v. So let us apply shortcut method u into v. So I get 1 minus x square as it is. Integration is sine of n pi x upon n pi, and derivative, and again integration. Okay, next again minus 2x, you take the derivative, which is minus 2, and then again you integrate, which is minus of n pi x upon n cube pi cube. The limits of integration are 0 to 1. Now, as we have seen earlier also, I'll substitute, if I substitute 1 over here, sin n pi 0, so this whole thing goes away. Same is the case for the third term. So now we'll substitute the limit minus minus minus, 1 minus you can take outside, and 2n upon n square is constant, so this also you can take outside. So I'm substituting the limit only in this term, okay, and this term x. So first I'll substitute upper limit 1 and cos of n pi. So that is cos of n pi minus cos of 0. So finally I'm getting minus 4 upon n square pi square and minus 1 raised to n. Cos of 0, it is 1. Okay, so cos, but again it is 0 into cos of 0, so anyway that this will become 0, it is not 1, because 0 into 1 is going to be 0. So the final answer for an will be minus 4 minus 1 raised to n square pi square. Okay, and since you know that your Bn is 0, so my final Fourier series will be a0 by 2 plus summation n goes from 1 to infinity. This an, what is the value for an? This is the value for an. And cos of n pi x by L, so n pi x by 1. So this is my required final Fourier series. I hope you have understood this.